So 3 minutes miss. Wait. Robert, please start recording. Today's experimental mathematics seminar speaker is our own Mr. Blair Seidler, who will talk about Boolean functions. As usual, you're always welcome to ask questions and then mute yourself back. Thank you.
Okay, thank you, Dr. Z. Yes, I'm going to talk about Boolean functions because that seems like the thing. So we had a few motivations for looking at Boolean functions of few variables. First of all, Boolean functions are cool. Hopefully we all agree on that. If you don't think Boolean functions are cool, you're probably in the wrong seminar. It's also, strategically, one of the things I really enjoy about working with Dr. Z is that he and I both like to hit small cases with a hammer and then maybe do some randomization and simulations to figure out some medium cases. And only then do we try to figure out what's going to happen in big cases that we can't brute force. We thought that, a catalog of all the circuits for small Boolean functions should exist, but, we couldn't find one. If you know of one that exists, please email me after the talk and let me know where it is, because I would be curious. And we also just wanted to have a set of tools for exploring Boolean functions because, there are other projects coming down the line, and, building a tool set up from scratch seemed like a reasonable investment. So the general idea of what we're going to do here is we start by creating an empty catalog, just list all the Boolean functions on n variables and admit that we have not yet found circuits for any of them. So that's what the NF is. Then we start with zero gate functions, generate all of the possible circuits on that many gates, figure out, just by throwing every possible input at the circuit, what function do you compute? And if we haven't found that circuit before, we say, okay, now we have a circuit that computes that function. And if we haven't found all the functions yet, add 1 to G, start over. So that's where we're headed. I think that, everybody in this audience is pretty comfortable with the definition of a Boolean function. We have some 2-element set. And, if we look at functions that map vectors in that set in some number of dimensions to the set, it's a Boolean function. In practice, we can use any 2-element set. Almost everybody uses 0, 1 for reasons that I'm going to touch on soon. I use -1 and 1 for false and true, respectively. And, here's the reason why we do that. This is the standard Hamming cube for K3, and everything is labeled with 0s and 1s. And I think that, everybody's seen this picture a bunch of times. But if you want to talk about subcubes of this thing, so here's a 1-dimensional subcube. In most of the literature, they'll talk about this as 1 star 0 or 1 dash 0 or 1B0 in a paper that I read recently. But I don't like having weird characters in my vectors. So by using -1s instead, I can use 0 to be I don't care. So now that subcube is 1, 0, -1, which is, x1 has to be true, x3 has to be false. I don't care what x2 is. And also, if I go to a 2-dimensional subcube, that's now the subcube 1, 0, 0. This is useful because one of the other projects that I'm not going to talk about this evening that I'm working on is I'm looking at implicants, prime implicants in Boolean functions. And it's nice to be able to figure out how big a subcube is by adding up the absolute value of the vector and subtracting from n. That makes me happy. So that's why we chose -1, 1. And, there are a bunch of different ways that you can think about a Boolean function. You can think of it as the subset of the Hamming cube where the function evaluates to true. You could just list the points. And in fact, in a lot of my Maple code, this is how I am tossing Boolean functions around. It's just, here are the inputs on which it's true. You can convert that easily enough. So I guess this is actually a full DNF, but I mean, this is a disjunctive normal form where it's got, 3 terms ORed together. You could simplify that into a nicer Boolean expression. You know, this is of course x1 and, you know, x2 ORed with x3. And you can take that reduced expression and translate it into some hopefully reasonably efficient circuit like that. So all of these are the same function. And I'm going to be mostly interested in the set of true points and the circuits. That's the two things I'm going to be trying to relate. So again, you know, the motivation for doing, you know, this set of true points is just now I can do a membership check. You give me an input vector, I say, hey, is that one of the things in my set? If it's one of the things in my set, then the function evaluates it true, and if not, it's false. There are times where I need to throw large numbers of functions around from procedure to procedure. So just to compact them a little, we do convert functions into integers. Each function has its own unique number. And, you know, that's definitely something that's going to come up later. The next major modeling decision that we had to make is how were we going to represent circuits? And, you know, we wanted something that would make it easy to generate them and also relatively easy to evaluate. So we chose straight line programs. There are a few different variations of this, but essentially a straight line program just doesn't have any loops or if statements or any of that. Every single line in the program is either reading an input or doing some operation on results of previous lines. And the output of the program is just whatever the output of that last line is. And what we're using as a definition of a gate is we're allowing it to be any of the 10 non-degenerate functions on two variables. So that's, you know, what we are going to use as a gate. There are other types of lines in the program, but they're, you know, either reading inputs or strange cases. So what do these things actually look like? Well, the basic gate types are if I have a line in my program that is just an integer and that integer is appearing, you know, so it's like if 2 appears on the second line of the program, it's just reading the second input bit. If a variable appears by itself on a later line, this is just the weird case where I want a way to represent the function that is just equal to one of its input variables. And the same for not I and true and false. These are really only used for the, you know, for the silly zero gate functions. The meat of every circuit is chosen from this set. These are the 10 non-degenerate functions on two variables. And, you know, these will show up on some line K in the program. And the 2 inputs have to be some lower line number. That's all that's going on here. So what does this look like? If I wanted to build a straight line program for this circuit that we saw before, I mean, what are the things that I need to do? First, I have 3 inputs, so I need to read them in. So effectively, I need lines in my program that are just, okay, here are my 3 input bits. The next thing that I need to do is compute that OR gate. So my 4th line is just going to take the results of lines 2 and 3 and OR those together. My next line is going to take the other input and AND it with the output of the OR gate. And that's what the program should do. And the maple encoding of this just is this. Read the first input, read the second input, read the third input, OR together whatever's out, whatever's on lines 2 and 3, and then AND together whatever's on lines 1 and 4. That's what that program says. Are we happy with this model? Pause for breath and a sip of beverage. Hearing no objections. Okay, so this is the haystack in which I'm going to be searching for my needles. And I want to know how big it is. So if we think about, you know, 4 variables and 7 gates, which seems a relatively modest size, anybody want to hazard a guess as to what order of magnitude this is for how many syntactically valid circuits there are?
10 to the power something.
10 to the something.
7.
Thank you, Dr. Zay. 10 to the what? Anybody?
10 to the power 7.
Okay, it's a little higher than that. We've got 10 choices for the gate type, and each input can be chosen from every smaller line number. So it's like, almost 4 times 10 to the 18th. This feels like a lot. I did a quick back of the envelope calculation, and I figured out that if I could process 23 circuits per second, that I could run through all of these in about the amount of time it's going to take the sun to turn into a red giant and swallow the earth. So this was probably not going to be a successful project. I'm hoping to graduate in fewer than 5 billion years. So we have to reduce the size of this, and
let me interrupt. In
Sure.
the grand scheme of things, this is peanuts. This is really essentially the proof that most Boolean functions have exponential size, super-polynomial size due to Shannon. Because our super exponential, a doubly exponential number of Boolean functions, and this is as big as it seems, is only exponential. Thank you.
Fair enough. So we'll come back to this later. This is actually where I spent most of my time, but we also need to figure out, do we actually want to look for all of the Boolean functions? So I don't. I didn't want to enumerate 65,000 of anything. So, I wanted to find, equivalence classes of functions, so that once we have a circuit for one member of the class, we have some nice way to convert it in every other member of the class. And there are a bunch of different ways to do this. The particular scheme I settled on was from a web page that I found, by way of OEIS. I was looking at sequences in OEIS, and there was a link to this web page by Tillman Peace, and it just had everything that I wanted to do. So I went there. And he's got 2 different types of equivalence classes that he talks about. He's got the small equivalence classes where 2 functions are equivalent if you negate some subset of the variables. And then he's got the big equivalence class, which is 2 functions are equivalent under any sign permutation of the input variables. So these are pretty standard things. These are the names that he chose. I went with those. So I'm going to talk about big equivalence classes. And, the number of Boolean functions and variables, these are probably very familiar numbers. These are just 2 to the 2 to the n, which grows ridiculously fast. And the number of big equivalence classes in OEIS sequence 616 is, a lot smaller, at least at the beginning. And, I didn't really want to look for over 1,000,005 variable functions because that was going to take a really long time, but 402 seemed a very manageable number. So that kind of became my target as soon as, I got to this point. So that was the goal. And, am I convinced that once I have a circuit for one member of an equivalence class that I can switch it over to a circuit that accepts other members of the class? And the answer is yes. And it's a pretty simple process. I can just leave the gate structure intact, so all the wires kind of go into the same places. If a gate has its output go to some other gate, I leave that alone. If I look at the permutation of variables, I just take any gate that has, I as an input, and I switch that input over to whatever the permutation goes to. And if I have to negate a variable, then the worst thing that can happen to me is I might have to change a gate type. So it's like if I have an XOR gate, I have to change it over to an equivalence gate. But since I have all of the non-degenerate functions, that's easy enough. So this is kind of the informal proof that yes, once I have one member of a back, I have all of them. And I also, in order to really take advantage of this, I wanted to be able to pick a canonical representative. So we're numbering the functions from 0 to 2 to the n minus 1. And again, I'm following Peace's lead here. I liked his numbering scheme. It had a lot of things going on. And he also had enumerated, the first, million of these or whatever in sequence 227723. So what does this numbering scheme look like? This is the 2 variable case, which is already a lot to throw on the screen. you just take the 4 possible input vectors in this case and just put them in numerical order. I mean, those are binary 0, 1, 2, and 3 if you're comfortable mapping negative ones to zeros in your head. And then if you just look at the outputs and read them from high order bit on top to low order bit on the bottom, you know, that binary number is the number of the function. So they are now numbered 0 to 15. And why this ordering is useful will come up, you know, when I talk about monotone functions. But for now, this is the ordering that we're using. Okay, so that reduces the number of functions I need to find. Now I have to start pruning the number of circuits so that, you know, I can maybe have my code run in some reasonable time. So the first thing is that there's no restriction in the syntax of my gates that forces I to be less than J, but it seems pretty clear that I can always have I less than J. If the 2 inputs are the same, then this gate is going to output a constant or its input or the negation of its input, depending upon gate type. And if I have a gate that does that, I don't need it. So obviously I can use a function with fewer gates then, a circuit with fewer gates. If I happens to be greater than J, I can reverse the inputs. 6 of my 10 gate types are symmetric with respect to their inputs anyway. The other 4 appear in pairs, and I can just swap gate types. So this seems like I can always get away with the first input being lower numbered than the second input. So the next, you know, slightly less obvious simplification, and maybe I should have drawn a picture here, but I didn't. So maybe I can do that now. There we go. What I'm talking about here is just if the structure of my circuit is, this is my output gate, and I have some blob over here, and I have some other blob over here. So maybe there's, you know, 3 gates in here and 4 gates in here, and I don't even know what they do. I hope that it's clear that I can write the same circuit, swapping the 2 halves, swapping the 2 subcircuits. And again, this may require a gate change type, but it's not going to have a major effect on the structure of the circuit. So, you know, the way I deal with this in the code is that, okay, now I'm still in annotate mode, actually. Sorry. Is I just, you know, when I'm recursively building my circuits, I only allow the first input to be a subcircuit with somewhere between 0 and up to half the gates. So if I'm building the 7 variable circuits, the left-hand side of my circuit will have between 0 and 3 gates always. And I don't lose anything there. Yep.
Blair, can I interrupt you for a moment? You asked
Sure.
at the beginning if anyone knew of earlier work on this subject.
Okay.
And I just interrupted, I just went away and got a book that was written in 1965
Okay.
by someone called Michael A. Harrison. And it's called Introduction to Switching and Automata Theory. And in the 1950s and 1960s, Michael A. Harrison, Department of Electrical Engineering at Berkeley, he wrote many papers about this, and this book, published by McGraw-Hill in 1965.
Yep.
And he has papers, many papers, classifying circuits, finite automata, Boolean functions, switching networks, and so on, using group theory, using Polier's theorem to enumerate them. There's really an enormous body of work. And he was just one of many people working on it, but he wrote his thesis on this in 1963 at Berkeley.
Cool.
And I suggest that you really should look at all his stuff.
I will.
Because
No, I think implicitly he does mention all this counting Blair mentions is in OIS, counting equivalent classes. This is essentially due to Harrison, who used Polier's theory to enumerate. So implicitly, Blair was aware of at least some of it.
I think that a lot of my references to Harrison are certainly indirect, possibly by 3 or 4 levels. But I might want to go back and look at where it started.
Yeah, maybe a good idea to look.
I like Neil's idea that I should go back to the source here.
Read
Particularly
the
because I like reading books that are older than I am. Okay. Thank you, Neil. So, one other, slightly less interesting optimization is just if I have a situation, again, I think that drawing this will probably be a little bit easier. If I have some gate here and one of its inputs is a gate and the other input is X1, and X1 also is one of the inputs here, I don't need 2 gates to do this. It doesn't matter what the gate types are. I think that this is also something that, a lot of these papers, have a proof of, that you do not need 2 gates in this case. So I do restrict that as well. Okay. So
can I ask a basic,
sure.
very basic question? So
Yep.
here, are you looking at circuits or are you restricting to formulas? Do you bound the fan out?
That's actually, fan out is what I am about to discuss.
Great, thank you.
So, I mean, I think fan out shows up on this slide. So the one corner that I cut in my very first pass at this was I went too far down the path, and I restricted if I had a 0 gate subcircuit, I restricted the input to be one of the input variables. But what that did is that effectively restricted the fan out to 1 when I didn't want to do that. Now, for circuits like 3 or 4 variables, this doesn't matter, but once you get up to 5 or 6, you want to be able to reuse gates. So, I didn't think this was going to matter too much, but it started mattering earlier than I thought it would. So, armed with that, my first pass on fixing this was to allow gate reuse and then say, okay, well, I have a 3-gate subcircuit here and I've allowed gate reuse, but I don't want to return the ridiculous number of circuits I'm returning. So let me just keep one that computes each subfunction. And that also turns out not to be enough because it has to be the right gate to be reused on the other side of the circuit sometimes. So, and while I was tracking down references, this is probably also a paper that is a great grandchild of Harrison. I found some, 2006 cryptography paper that had a bunch of numbers. And this was the first time that I actually seen somebody write down the numbers of circuit complexities in something that was on my reference chasing path. And I had, in fact, identified 3 classes of functions that's complexity 7 that should be complexity 6. So I know that I have an issue. In theory, it was easy to fix, which is all I needed to do is allow 0 gate subcircuits to be line numbers lower than the current line. And in practice, I got back to an uncomfortable number of circuits. So, once I allow gate reuse, now 4 variable 6-gate circuits blow up to about 42 billion, and the 7-gate circuits is back up to 5.4 trillion, which is 6 orders of magnitude what I started with, but still not great. I did manage to do one clever thing that I think isn't helping enough based on the fact that my code is still running. What I did do is I split out the structure of the circuit without worrying about gate types. And then I go back and, plug in the gate types to each gate. So I don't have to keep all of these things in memory at once, which was making the compute server at Rutgers very unhappy with me because that was way too much memory and way too much swap space. So what I did is now I have, for the 6-gate case, I only have 42,000 circuit shapes. And then each one of those, there's a million ways to assign the gates. So that's a little bit better. So what do my numbers look like? Well, this is how many big equivalence classes I came up with each circuit complexity. the two entries in the table here with stars do not agree with Saarinen enumeration. You know, I have code running that will presumably change those numbers to, I'm thinking 133 and 23 by the time it's done. This may be slightly less interesting than the number of functions. The number of functions available here is, you know, again, the last two entries here, this last one should be not 2944, but 2720. So there are 224 circuits that I currently have misclassified. The first two numbers are also off, but they're only off by definition because I think in Saarinen's enumeration, he counted not as a gate and I don't. I count not as a zero gate circuit. So, you know, I think in his work, you know, those numbers are 6 and 64. Okay, so which functions are the hardest? This is one of the, you know, questions that I was, you know, hoping to get to when I started this. And there are only 3 big equivalence classes on 3 variables that have the maximum complexity. And one of them is the exactly to function. One of them is the majority function, which always seems to be a pain to compute. And 107 is this weird function that's exactly one input or specifically x1 and x2, but not x3. So, you know, if you look at, you know, the majority function, the particular program that my algorithm found, you know, is this string of maple code, which nobody wants to look at. So I've translated into human below that. It's, you know, take the first 2 inputs, XOR them, take the first and third inputs, XOR those, and the result XOR with X1. And there are other ways to compute the majority function with 4 gates, but you can't do it with 3. That was the point. Now, the next thing that we jumped into here was I decided to look at monotone functions.
And so the exclusive ORs seem to
Yep.
be the most expensive ones or things involving them, right?
I mean, it is, but it depends upon your computational model. I mean, for, you know, for the way I am actually, you know, computing in circuits, I don't think XOR costs me more than anything else does because it's a call into the same procedure. I know that when you're getting down into the electrical engineering, yes, XOR gates are more expensive. I could probably find other circuits that do this, which might have fewer XORs, but they may have more gates. So,
Thank you.
So I next, you know, decided to look at monotone functions. These are kind of the standard definitions, which I believe I took directly from Kramer's book on Boolean functions. I just changed the notation to match my silly negative ones. So, you know, a positive function is positive in each of its variables. A monotone function is monotone in each of its variables. And, you know, here is, you know, the big exclamation point. I hope Neil is still here to see this slide. But during this project, I did get to spit my first ever sequence to OEIS. It is specifically a subsequence of 227723 with the big equivalence class representatives for the monotone big equivalence classes. So that was, you know, a pleasing moment during this process. And, you know, one of the nice things, you know, this is kind of where everything kind of came together for me is because of the ordering of functions in, you know, piece numbering, the functions that I get as big equivalence class reps always are positive functions, which means that when I'm looking through them, I only need and and or gates. I don't need to worry about negation. I mean, you never really need to worry about XOR gates in a monotone function, but, you know, the fact that I only needed 2 gate types was nice because it dropped the exponential growth of the number of circuits. You know, so now I'm dealing with 2 to the G's instead of 10 to the G's, which, you know, from a theoretical perspective is not that interesting, but from a practical perspective, it's great. And in addition to the, you know, reduction on the types of gates that I needed, there are also just a lot fewer big equivalence classes of monotone functions. For n equals 5, you know, there are, you know, over 1 million big equivalence classes, but there are only 210 monotone equivalence classes, which is nice. And the number of monotone Becks is another wonderful OEIS sequence, happens to be the Dedekind numbers. And the reason for that is I think described if you follow enough of the links off of the OEIS page, but it's really just because there's a bijection between anti-chains and positive Boolean functions. And if you look at, sequence, I think it's 372 is the labeled anti-chains, and that corresponds to the overall number of monotone functions. This sequence is unlabeled anti-chains, which corresponds to equivalence classes of monotone functions, and it's basically the same thing. So, and the reason for that is simply that you can think of any monotone function as look at all of the minimum points at which a function is true. And that as an anti-chain, that anti-chain specifies a particular positive function. Okay, and this is what I have found now. Again, I need to go back and make sure that all of my gate reuse stuff is correct and make sure that these match other known results. The strangest result here, from my perspective, is that there was one function that required 13 gates and no other function required more than 11. Anyone want to hazard a guess what the 13 gate function was? Robert doesn't want to guess. No? Okay. It is, strangely enough, the majority function, which always seems to turn up in these things. So, I mean, I have more things to do, and thanks to Neil, I now have more things to read. But I do have, a write-up of what I did on my webpage. I will obviously be updating it with the new things that are coming. And I just want to thank Dr. Z for, all of his encouragement during this thing, and to all of you for listening to me talk.
Thanks for this preliminary but very interesting account of your ongoing research to catalog all the small circuits, all the circuits of Boolean functions. We have time for questions. Any questions from the audience?
Blair, did you say that some of your code is running right now?
Yes.
Is it running on the same computer you're giving the talk from?
No.
Okay. Could you, I forget, could you explain what is still running right now? What is it trying to catalog?
Well, what I did was,
Is the family it's trying to enumerate?
I'm specifically running the case for 4 variables and 6 gates, which is, these 42 billion circuits that I kind of need to sift through to find the error in my previous runs. And if it makes you feel better, it's running on the department's compute server. It's not running on my laptop, because that would take even longer.
So is any hope to do the same thing for 5 variables, or it's beyond the scope of computers?
I mean, if I wanted to do this for 5 variables, I think that, there are a few other types of pruning that I would need to do, because right now running through the circuits is just taking too long. One thing that occurred to me is, like, if I see the same gate twice in a circuit, obviously I can throw it out, but I think that I need to be more clever in the generation. I think that I need not to, generate, every circuit. I need to generate ones that, don't have the same things happening on both sides of the circuit ever. Because right now, I don't think about that much. There's not a lot of intelligence.
So can I ask another question? So if I give you a truth table and a candidate circuit that I claim is smallest, do you have any efficient way of checking that the circuit that I'm giving you indeed is the smallest size circuit that realizes a given Boolean function, other than brute forcing?
Well, The answer to that is currently no, except that, I now have a catalog. So if one exists, I could just look it up. If you talk about, give me one circuit for, for say a 7 variable function and ask, is there a smaller one that exists? No, I do not currently have a way to do that.
I see. Thank you.
And Blair, the straight line complexity is the same thing as circuit complexity, right? There's a canonical way of mapping one to the other.
Right. That was, by design. I'm trying to match, the old papers like Bloom and Zwick and all the ones that were showing things like 2.5n and 3n and 4n complexity all tend to use this model where they allow any non-degenerate 2 variable function as a gate and they treat them all equally.
Thank you. Are there more questions to Blair? Well, thanks for coming and thanks for a very interesting talk. Let's thank Blair again. Robert, please end this meeting. Thank you. Bye-bye. And see you next week, where